So we've already learned Boyle's law, Child's law, and Gay-Lussac's law. And these show the different relationships between pressure, temperature, and volume. Boyle's law shows an inverse relationship between pressure and volume, meaning when you increase one, the other decreases, and vice versa. Child's law and Gay-Lussac's laws are both direct relationships. Child's law dealing with volume and temperature, where if you increase the temperature, the volume will increase as well. It's kind of common sense that when something is heated, it expands. There's a lot of applications of that in the real world. Gay-Lussac's law as well, where as you increase the temperature, the pressure is going to increase. And this is going to be because the molecules will be moving faster, because temperature is a measure of the average kinetic energy. And when they're moving faster, you're going to have more collisions with the walls of a container, which is what pressure is. And they're going to be hitting the walls harder. So that also is a direct relationship. When you put these three laws together, you end up with the combined gas law. And this problem can be used to solve any changing gas, any problem with a changing system for a gas, as long as there's the same number of moles. So I put a problem on the board here where I have a balloon at a certain temperature, volume, and pressure. And then what we're going to do is figure out what the volume would be at a different temperature and pressure. So in this case, the balloon starts with an initial temperature of 500 Kelvin, an initial volume of 4 liters, and an initial pressure of 2 atmospheres. And we're going to find what that goes to at STP. So standard temperature and pressure tells us it's 1 atmosphere worth of pressure, and it's at 273 Kelvin. So I've set this up with the black lettering will represent the initial situation, and I'm going to use a green circle to indicate the things that are in the second situation. So these are all initial conditions. That's my initial temperature, this is my initial pressure, this is my initial volume. Okay? So these are the 3 pieces of information we're going to need in this problem. And my final situations are the standard pressure and temperature, so this will be P2 and that will be T2. And then we're looking for what the volume will be. So this is our question mark, and that's what our final volume is. It's our question. So whenever you're solving for a variable in an equation, you want to get it alone and on the top. It's already on the top, so now all we have to do is get it by itself. So before we plug in any numbers, I'm going to rearrange the equation. I'm solving for V2. So in order to get that by itself, I'm going to multiply it by the reciprocal of everything else on that side. So it's going to be T2 over P2. And in algebra, whenever you do something to one side, you've got to do it to the other. So here we go. Now your P2 and T2 will both cancel out. And when you end up with the equation, the final volume is going to equal to the final temperature times the initial pressure and initial volume divided by the final pressure and the initial temperature. Then at this point what you can do is plug in all the variables that you have in order to solve the equation. So T2 is 273, P1 was 2 atmospheres, 273 Kelvin, P1 is 2 atmospheres, and V1 was 4 liters. And that's all going to be divided by 1 atmosphere worth of pressure and 500 Kelvin. So you're going to see when we do this problem, the units that cancel out are Kelvin and atmospheres, and our answer is going to be in liters. Now at this point, do you have a calculator real quick?
Top right drawer? Nope. Oh, the desk, sorry.
Yes, sorry. Okay, so 273 times 2 times 4 divided by 500, and we'll get that our volume will be 4.368 liters at standard temperature and pressure.